Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory combinatorics based on my book, An Invitation to Combinatorics. The subject of this lecture is the characterization of trees, and this is a lecture in the graph theory section of these lectures. So let's get started. So the main goal of this lecture is to prove a characterization of trees. So what I'm going to prove is the following theorem, that if you have a simple graph, then the following facts are equivalent. I'm not saying any one of these things are true for a graph. I'm just saying that if any one of them is true, then so are all the other ones. So the first one is that G is a tree. A tree is a connected graph with no cycles. The second one is that any two vertices of G are connected by a unique path. The third one is that G is connected and every edge is a bridge. The fourth one is G is connected and the number of edges is one less than the number of vertices. When you put an absolute value sign around a set, then that means the size of that set. The next one is that G has no cycles and the number of edges is one less than the number of vertices. And the last one is G has no cycles, but if edge is added to E, then the resulting graph will have a cycle. Now, a lot of things are repeated here, it seems. The point is not that a tree has these properties. It does. If that's all I was going to say, I wouldn't say that I wouldn't repeat the fact that it's connected or the number of edges is one less than the vertices several times. The point is that these statements are equivalent. If you know any of them, then you know all the other ones. If you know any of them to be false, then all the other ones are false. I will remind you of all the definitions. I have a video before this that talks about the vocabulary that's needed in more detail. So a simple graph is a pair of sets V and E. V is a non-empty set of vertices, and E is a possibly empty set of edges. And each edge is a pair of vertices. Each edge is what we think of as two vertices being connected. A multigraph is a graph with repeated edges. And in this case, E, the set of edges, can be a multiset. Instead of having just, you could have repeated edges. The same edge, the same pair of vertices could appear in E more than once. A general graph is a graph with repeated edges and loops. And so in this case, an edge might be something like 7, 7. A loop from 7 back to 7, where 7 is one of the vertices. In a general graph, a walk joining x0 and xm is a sequence of edges that starts with x0 and something, x1, and then x1 and something else, and so forth. Another way of writing a walk would be just to not write the edges, but write the vertices, x0 to x1 to x2 to xm, and so forth. Either one of these works pretty well. If you actually have a multigraph, if you have double edges, then there might be some confusion. And actually, the best way to write a walk is to think of it as a vertex, then an edge, a vertex, then an edge, a vertex, then an edge, and so forth. And one can use any one of these ways of talking about a walk. Now, if you start from the same point as you end, then you say your walk is closed. And if you don't, then you say you have an open walk. There's some vocabulary associated with this that I will want to remind you of right now. This was subject of a previous video. So a path is always open, doesn't begin and end at the same place, and there's no repeated vertices or edges. A cycle is always closed, but also no repeated vertices or edges. So paths and cycles, they have no repetition of any kind, and one is always open, one is always closed. A trail, it could be open or closed. You don't have any repeated edges, but repeated vertices are okay. If you have a repeated edge, by the way, you will have to repeat a vertex. But if you have repeat vertices, you don't have to necessarily repeat edges. A circuit is always closed, but also no repeated edges, but you allow repeated vertices. And the most general thing of all is a walk that could be open or closed, and you can repeat anything you want or not. Again, this was a subject of a previous video where I gave examples and talked about this in a little bit more detail. One lemma that we have proved is that if you are in a general graph, and if you have two vertices, and if there's a walk between them, then there's a path between them as well. If there's a walk, there's a path. The proof of this was in a previous video, but the idea is pretty simple. If you have a walk going from x to y, and if it's not a path, then that means some vertex was repeated. Well, just trim the part of the walk between those repeated vertices and do that as many times as necessary, and you will get a path. An edge in a general graph is called a bridge if its removal increases the number of connected components. So what's a connected component? It's a bunch of vertices that you can go from any one of them to any one of them using a walk, and you can't go to anything outside of that group of vertices by a walk. And if a bridge is something that if you take it out, the number of connected components increases, that some parts of the graph that were previously connected to each other now become disconnected. And a lemma that we proved about this in a previous video is that if you have a connected general graph and you have some edge is again a pair of vertices, then this guy is a bridge if and only if no cycle contains alpha. So if you're a bridge, you can't be on a cycle, basically because if you're on a cycle, then there's another way other than that edge to go from one end to the other, and therefore removing that edge is not going to disconnect the graph or increase the number of connected components. Another way of saying the same thing, and the other way around also, is that if you don't have any cycles, you've got to be a bridge, because if you weren't a bridge, and if you take the guy out, then there got to be another way around which would have created a cycle. I mean, that's sort of basically it, but you should watch the other video if you want more detail. Another way of saying the same thing is to look at the counterpositive and to say alpha is not a bridge if and only if alpha is sitting on a cycle of G. With all the results that I will tell you, the best thing to do is stop the video and try to prove it yourself. And the way to do that is to draw some examples and try to come up with a counterexample to the thing you want to prove. And along the way, you will come up with a reason for why it might be true. Now, your proof might not be quite formal. It might not have, there might be some subtle issues that you didn't take care of, but you might have a very pretty good intuition about why it might be true. And then if you watch the video after that, then you will see how well you did. Now I want to talk about the number of edges in a connected graphs. So these are all preliminaries to that general theorem about trees. So let's say that you have a connected simple graph. Connected means that you can walk from any one of the vertices to another, and the number of vertices is n. So I'm sitting here, a connected graph, simple graph walks through the door, and I know the number of vertices is n. And the conclusion is that without checking anything, I know that the number of edges must be greater or equal to n minus 1, one less than the number of vertices. Now, it might have more edges than that, but it will have at least n minus 1 edges. And in fact, there are connected graphs where the number of edges is one less than the number of vertices. And for such graphs, for these extremal graphs, the ones that have just the minimum number of edges that you need to be connected, every edge is a bridge. Now, I said this theorem for a simple graph, but I could have well said it for general graph, because in a general graph, in addition to the usual edges, you have double edges and loops. But double edges and loops are not helpful in terms of making a graph connected. So if a graph was not connected, adding a double edge or a loop is not going to make it connected. So those are extras. So if the theorem is true for simple graphs, it automatically, with a vengeance, will be true for general graphs, because those loops and double edges were just extra. You can throw those out, and you still will have n minus 1 edges. Putting those back in will give you even more edges. But in the case that it's a general graph, then I can even say more. I can say that if you have the number of edges is one less than the number of vertices, then the graph is simple. Then I can add that fact in. And here are some examples of graphs that the number of edges is no more than one less than the number of vertices. Any path is like that, and some of the things called a star, one vertex with a whole bunch of edges coming out of it. Both of those have the number of edges is one less than the number of vertices. So there are graphs like this. So how are we going to prove this? So what is it that we want to prove? We have a connected graph. We have the number of vertices is n, and we want to show something about the number of edges. We want to show that the number of edges is n, at least n minus 1. And we want to show that if the number of edges is actually n minus 1, then every edge is a bridge. That's what we want to prove. So whatever graph it is, so one graph, as I said, the graph has walked through the door. I know the number of vertices. I want to see, why is it true that it must have at least n minus 1 edges? And I think about the way I'm going to draw that graph that walk in. I will start with n isolated vertices and then slowly put the edges in. And the point is that at the beginning, when you have these n isolated vertices, you have n connected components. And when you add one edge at a time, every time an edge connects two vertices. So at best, it'll bring down the number of connected components by 1. It can't do more than that. So when the first edge you put in, the number of connected components goes down by 1. The next one go down by 1 as well. and so forth. Sometimes it might not go down by one at all, because it might be that you're connecting vertices that were already connected through some other path. But at best, each additional edge decreases the number of connected components by at most one. And therefore, to get from n connected components to one connected component, you at least need n minus one edges. Because again, you start with n connected components. Every time you're going to go down by one. So how many edges do you need to, if you're super efficient, to get to one, you need at least n minus one edges. Now, what about if you actually needed n minus one edges? Well, then that means that every one of those edges that you put in had to do its job. Every one of them had to bring down the number of connected components by one. You didn't have any room to spare. It wasn't like any one of those edges along the way could sort of take its time and say, well, I'm not going to do anything, and the number of the connected components is going to stay the same. If that happened, you needed more edges. But this time you have only n minus one edges, the least number you needed to bring it down to one. So every edge, when you add it in, should have decreased the number of components by one. Now, if you reverse the process and start from the other end and start deleting, it must be that every edge, when you take it out, the number of connected components increases. In fact, in our first proof, the order of putting the edges in doesn't matter. So if there's one edge that you're wondering, are you a bridge or not, you might as well put that edge in at last. And that last step that you put that edge in, the number of connected components went from 2 to 1. So now if you take that edge out, then the number of connected components will go from 1 to 2. And therefore that edge, that the one that you wanted to prove is a bridge, is a bridge. And you could have done that with any of the edges. So every edge is a bridge. So I'm going to now prove something very similar. I'm going to say that if G is a connected simple graph, then every edge is a bridge, if and only if the number of edges is one less than the number of vertices. You might say, well, didn't we just do that? Well, we did one direction. We just proved that if the number of edges is one less than the number of vertices, that extremal number, that minimum number that we needed to make a graph connected, then every edge is a bridge. That's what we proved. But we didn't prove the other way around. Again, stop the video and try to prove the other side. So to prove the other side, I'm going to induct on the number of vertices. I'm going to use induction on the number of vertices. For induction, you have to do a base case. So the base case here is going to be if n is 1, the number of vertices is 1. If the number of vertices is 1, is every edge a bridge? Well, automatically, if there's only one vertex, there can't be, because this is a simple graph, there can't be any edges at all. And so every edge is a bridge. If you tell me any of the edges of this graph, there aren't any, but if you give me any of them, it is a bridge. And moreover, the number of edges is 0, which is 1 less than the number of vertices, exactly as what we would have wanted. So the base case is fine. So now for n greater than 1, we're going to use induction. So we're going to assume that we already know the theorem for smaller graphs. Smaller in what sense? Because we're inducting on n, the number of vertices, smaller in the sense that if a graph has fewer vertices than the one we're looking at, we assume that the theorem is true for that. So let alpha be any edge of your graph. If the graph doesn't have any edges, then it won't be connected in that case. So let alpha be any edge. And look at the graph when you take that edge out. So G prime is that same graph, but taking that edge out. But so this new graph has n vertices. I didn't take any vertices out. I just took one edge out, and has one less edge than before. Now, alpha was a bridge because every edge was a bridge. And so this G prime went from being a connected graph to a graph with two connected components, G1 prime and G2 prime. Now, I don't know how many vertices went to G1 prime, how many went to G2 prime. So let's say K of them were in G1 prime, L of them were in G2 prime. But whatever those are, this K and L will have to add to N. That was the number of vertices that we had. And they're both less than N. The fact that they're less than N means that these are graphs that I can use induction on. They're smaller graphs. They have fewer vertices. And every edge in each of those is a bridge because nothing has happened to the bridgeness of the edges. It used to be a bridge before in the bigger graph. Now that we have just taken one edge out, the other guys are still a bridge. And so I can apply induction. And so now I know that G1 prime has K minus 1 edges because it has K vertices. It has one less edge. And G2 prime has L minus 1 edges. So how many edges did our original graph G have? Well, the number of edges in G is the ones in G1 prime plus the ones in G2 prime, plus, let's not forget about alpha, because alpha was the guy that we took out. So this is the total number of edges. But if you add those out, one of the ones cancel out, and you get k plus l minus 1, and k plus l was n, so you get n minus 1 as we wanted. So we proved that if every edge is a bridge, the number of edges is 1 less than the number of vertices. So now let's turn to trees. Some of these things that I proved, I'll remind you again, and I'll put in that one big theorem. It will be easier to remember them. A simple graph is a forest if it has no cycles. Any graph that has no cycles is a forest. And it's a tree if not only it has no cycles, but it's also connected. So a forest is, its connected components are trees. Forest is made up of trees. So for example, here's a tree, and if I have 3 of those or a number of those, then I get a forest. So now we're dealing with our main theorem, the theorem that this lecture is about, that if you have a simple graph, then the following are equivalent. Now, it's important to understand that I'm not saying that the following things are true or false. All I'm saying is that if any one of them is true, then so are all the other ones. The first one is that G is tree, that it's a connected graph with no cycles. The second one is that there's a unique path between every pair of vertices. The third one is G is connected and every edge is a bridge. The fourth one is G is connected and the number of edges is 1 less than the number of vertices. The fifth one is G has no cycles and the number of edges is 1 less than the number of vertices. And the sixth one is that G has no cycles, but if any edge is added to E, then the resulting graph will have a cycle. Now, you might say, well, why are we repeating things? Like, why are you saying the number of edges is 1 less than the number of vertices twice and connected twice and so on? Well, the point is that each of these is a separate statement. And I'm saying that if you have a tree, then all of these things are true. If that's all I wanted to say, then I wouldn't have repeated myself. But I'm saying that if any of these are true, then you know all the other ones. So a graph walks through the door, you might just know that it's connected and the number of edges is 1 less than the number of vertices. If you know that, then you also know that it's a tree, that every edge is a bridge, there's a unique path between every 2 vertices, and so on and so forth. So each one of these is a criteria that you could use on the graph of your choice to see satisfies all the other ones. Now, some of these might be familiar. We've seen the number of edges being 1 less than the number of vertices. All of these things sound familiar because some of them we've already proved. Now, how am I going to prove that all of these statements are equivalent? Do I have to assume any one of them and then prove that all the other ones follow from it, or assume any one of them is false and then prove all of the other ones is false? I don't need to do that. In fact, what I will do is I will prove these set of implications. So I'll prove that 1 implies 2, 2 implies 3, 3 implies 5, 5 implies 1, and then 2 implies 6, and 6 implies 1, and 3 and 4 are equivalent. And in fact, some of these we've already proved. And if we do that, then if you know any one of the statements, then you can find your way through implications to any of the other ones. And in fact, if you know any of them is false, then you know all the other ones are false as well. So for example, if one is false, why is 2 false? Well, if 2 wasn't false, it would be true. But if it was true, then 3 would be true. And if 3 was true, 5 would be true. And if that was true, then 1 would be true. But 1 was false. So 2 could not have been true. 2 must have been false. And so those are just the counterpositives of the same statements. So let's get started. First, we're going to prove that 1 implies 2. So we assume that we have a tree. So that means a connected graph with no cycles. And we want to prove that every 2 vertices are connected by a unique path. Well, pick 2 vertices. Are they connected by a unique path? Well, they're connected. The graph is connected because it's a tree. So there is a walk from V to W. And if there's a walk, there is a path. And so there is a path. But why is it unique? Well, if there were 2 ways to go from V to W, 2 distinct paths from V to W. So for example, maybe look at the graph on the bottom left. So maybe there is one path and then there's another path. If you think about it, and as I said, try to prove this yourself. You might say, okay, if I go from one way from V to W and another one from V to W, then they form a cycle. Well, that's not quite right, because it might be that these paths share some vertices and in fact some edges. So leaving V, the 2 paths may share vertices. So let X be the last the vertex they share. So up to X, they sort of went together. I mean, they might have gone to the different edges, but that's the last vertex that they share. And Y is going to be, maybe they come back together all the way at W, but maybe not. Maybe the 2 paths get together earlier. So let Y be the first time after X, the 2 paths gets together. And so if you do that, then you have a cycle going from X to Y on one path and coming back from Y to X on the other one. And but we had said that trees do not have cycles, and so that's a contradiction. So we assume that there's two paths, these different paths from V to W, and we prove that if that's the case, you must have a cycle, and therefore it can't be a tree. So we proved that if you have a tree, then every two vertices are connected by a unique path. The next one is that we want to take statement 2, that every two vertices are connected by a unique path, and prove that G is connected and every edge is a bridge. Now, we can't assume now that G is a tree, and like we don't know anything about that. All you know about your graph is that every two vertices are connected by a unique path, and the thing you want to prove is that the graph is connected and every edge is a bridge. Well, there's a path between every two vertices. In fact, there's a unique path, so therefore the graph definitely is connected. But why is every edge a bridge? Let's look at an edge and assume that it's not a bridge. Well, if it's not a bridge, then that means that if you take that edge out, the remaining graph will be connected. And so that means that there's a path from V to W that doesn't contain alpha, because you took alpha out, but still you have a connected graph. So you must be able to go from V to W in some other way. But alpha is also a path from V to W. So that gives you two different ways to going from V to W. One using just alpha, that's just a little tiny path, or this other path that's there in G minus alpha. But that was not what we had. This is a contradiction, because we had assumed that every two vertices are connected by a unique path. And so our original assumption must have been wrong, because our argument was correct, that we had assumed that alpha is not a bridge, but that must have been false, and alpha is a bridge. So this is a proof by contradiction again. Now I want to talk about 4, 3, and 5. So 3 is G is connected and every edge is a bridge. 4 is G is connected and the number of edges is 1 less than the number of vertices. And 5 is G has no cycles and the number of edges is 1 less than the number of vertices. And I'm claiming that we've already proved these. Why? Well, because we already proved that if you have a connected simple graph, then every edge is a bridge if and only if the number of edges is 1 less than the number of vertices. That was earlier in this lecture. We proved that. And that already proves that 3 and 4 are equivalent. So the equivalence of 3 and 4 we already proved. We also proved that if you have an edge, it's a bridge if and only if no cycle of G contains alpha. And that shows that 3 implies 5. Because if every edge is a bridge, that's what 3 tells me, then you're not going to have any cycles. Because if you had any cycles, then the edges on those cycles would not have been a bridge, and every edge is a bridge. And because every edge is a bridge, by that first fact, we know that the number of edges is 1 less than the number of vertices. So these two facts together tell us that 4 and 3 are equivalent, and 3 implies 5. By the way, from this, it also follows that if you actually have a tree, then every edge is a bridge and the number of edges is 1 less than the number of vertices. Because from a tree, we prove that if you have a tree, there's a unique path between every two vertices. And we prove that if you have a unique path between every two vertices, the G is connected and every edge is a bridge. So if it's a tree, then every edge is a bridge. And now we prove that if you know that, then you know that the number of edges is 1 less than V. I mean, we didn't just prove that, we had already proved that. So the point is that for a tree, we already know these facts. So what remains to be done is assume that we have no cycles and the number of edges is 1 less than V, and prove 1, that we have a tree. So again, here, all I know is that a graph walked through the door and I checked and it doesn't have any cycles, and I know the number of edges is 1 less than V, and I want to prove that it's a tree. Now, if it doesn't have any cycles, that's a good thing, because that's a part of the definition of a tree, but I have to prove that G is connected. So if the number of edges is 1 less than the number of V and G has no cycles, why is it connected? So maybe it's not. I will let K be the number of connected components. And I want to show you that there's only 1. Now, G has no cycles, so it must be that it's a forest. And so that means that every connected component is a tree. And for each of these trees, we just argued that we know that the number of edges is 1 less than the number of vertices. Now, so every one of the trees in this forest has 1 less edge than it has a vertex. So if you go around and ask, okay, how many edges do you guys have? How many edges you have? How many edges you have? If you go through the K connected components, every time you ask that, you fall behind. The number of edges falls behind the number of vertices by 1. So the total number of edges is the total number of vertices minus K, because there's K components. But what we know actually is that the number of edges is number of vertices minus 1. So that means that K is 1, and so the graph is connected. So this is sort of a nice proof. So the only thing remains is to talk about condition 6. So one thing we want to prove is that if you have a graph and all you know about it is that it has no cycles, but if any edge is added, then you get a cycle. That's the thing you know about your graph. Then we want to prove that it's a tree. So that's one thing we want to prove. What do we have to prove? It doesn't have any cycles. So again, we have to prove it's connected. So how do I know that? So pick two vertices. How do I know that there's a way to go and walk from V to W? Well, maybe there's an edge. The VW is an edge of the graph. Well, if that's the case, well, certainly I can go from V to W. But if there isn't, then add it in. Put that edge in. Yeah, well, you get a new graph. But this new graph, we have added in the edge to G. So this new graph has a cycle. And that cycle will include that edge that you put in. But it has that other rest of that cycle. And the rest of that cycle will give you a path from V to W. So V and W, those two vertices, are in that cycle. One of them is this edge that you added in that wasn't really there. But the rest of that cycle was all vertices that was in the graph. So there was a way to go from V to W. And therefore, we have a connected graph, and therefore we have a tree, because we already know G has no cycles. The last thing we want to prove is that if the statement 2, meaning that if you know that there's a unique path between every two vertices, why is it that 6 is true? That G has no cycles, but if an edge is added, then you get a cycle. First of all, if you have a cycle, pick any two vertices on that cycle, and there's two paths between them. One going one way on the cycle, the other going the other way between on a cycle. And so because we know there's a unique path between every pair of vertices, there can't be any cycles because there's two ways to go from on a cycle. On the other hand, if you add an edge, that edge together with the path that we know, that unique path between two vertices, will give us a cycle. So it's true that G has no cycles, but if you add any edge, you will get a cycle. So let's recap. Some of the things we proved is about trees. So we proved that if G is a tree, then it's connected, has no cycles. Well, that's the definition. But also that every edge is a bridge. The number of edges is one less than the number of vertices. And there's a unique path between each pairs of vertices. And adding any edge creates a cycle. Trees are really important because not having cycles, for example, in computer science, when you want to do algorithms and so forth, trees come up quite a bit. And knowing different characterizations of it can be useful. But we proved more than just prove properties of trees. So these are actually ways of deciding if something is tree. The first thing I said was that if you know something is a tree, then you know stuff about it. But even if you don't know anything about a tree, and if you know any of these other facts that we proved, then you know it's a tree and it has all the properties. This is the end of this lecture. If you like to be subjected to videos like this, then subscribe or like my videos and keep hydrated at all times.